last time we introduced the finite volume method, and we talked about calculating the fluxes at the faces of these control volumes. So we had a diffusive flux, and then we said we can just use a second order approximation, so phi east minus phi west over delta x. Convective flux could be an average between the two cell center points or an upwind value. So the value of the convective flux at the east face, we could set that equal to the value at the cell center. So u phi lowercase east is u phi east. A number of these, but essentially, that we're going to talk more about these things as the semester goes on. But you can just use these standard two approximations for diffusive flux and the convective flux. But we didn't talk about boundary conditions. And in the general finite volume formulation, we can apply general Dirichlet and Newman conditions. With a Dirichlet condition, what is a Dirichlet condition? You specify a value at the boundary. Okay? Now, in the control volume formulation, we said, in general, we're going to store the average value of a quantity at the cell center if we're going with a single value approximation for the integral. Okay, so we're going to store the average value of phi at the cell center. This is a left boundary, for example. And imagine the value in general. That's what you specify. You specify when we say we specify the boundary condition, you're specifying the value of phi for a Dirichlet. You're specifying the value of phi at that boundary, not here, not anywhere outside. Okay. So then we don't have a degree of freedom at the face, right? Because the degree of freedom is here. We're solving for these values at these cell centers. So we can't really directly access this value. But one strategy that's up to second order accurate is to use a ghost cell. So we saw the ghost cell concept where you can store temporary values to allow speedy and easy calculations. And we can use the same concept here, and we can imagine that there exists a ghost value outside the computational domain such that the average of the interior and the ghost, in this case, so that's a second order approximation, produces the ghost cell value. So mathematically, this says phi interior plus phi ghost equal to the specified value. So that allows us then to set a value in phi ghost such that up to second order, we reproduce the correct value at the boundary. Okay? So in this equation, phi ghost is unknown. We don't know phi ghost. We know phi, that's specified by the user. Phi interior is known from the previous time step. Okay, that's phi old, essentially. Okay? So you take those, you average, and then you can set phi ghost equal to 2 times phi minus phi interior. Okay, that's how we do Dirichlet conditions. Okay? For Newman conditions, you specify a flux at the boundary. And yeah, so this is incorrect here. Sorry, I didn't update those. But you specify a flux at the boundary. Now, and you said that d phi, you say that d phi by dn is equal to capital Phi. And then in this case, what you can do, you can set the phi ghost, for example, to produce a d phi by dx. So you say, so this is incorrect here. You say d phi by dn, or d phi by dx in this case, is phi interior minus phi ghost over delta x. Okay, and then you specify phi ghost using phi interior and capital Phi. I'll fix this before I post the notes. Sometimes certain variables, or when you're setting the flux, you can set it directly on the boundary, because the great thing about the finite volume method is you store the fluxes at the boundaries, right? So if you're given this flux, that's a diffusive flux essentially. You can just set that flux directly. Whichever method you want, they're going to be okay. So it's sometimes just easier to do phi ghost because that doesn't violate the loop, your for loop. You're just looping over all cells in the interior, and you're doing the same calculation, okay? Rather than saying, I'm going to loop over the interior points, and then at the boundary points, I'm going to go and set the fluxes over here. It's just going to mess up, make the code a little bit less cleaner, okay? We'll be dealing with a lot of that pretty soon. Okay. So now we're going to take the finite volume formulation and with a single integration point on a structured grid and we're going to apply it to the Navier-Stokes equations, okay? And we're going to stay within the context of the staggered grid. We spoke earlier that the staggered grid makes more sense to enforce the discrete divergence-free condition. And we saw how the checkerboarding occurs because div grad is not equal to del squared, et cetera. And one of the remedies was the staggered grid, among other things, and the diff stability condition. But today I'm going to also show you an even more intuitive and natural way where the staggered grid arises. Okay? So first recall the incompressible constant density Navier-Stokes equations. We're dealing with 2D, but the same thing applies in 3D. It's just an extension one more direction. Mass conservation, the integral over the surface of a control volume, u dot n ds equals 0. X momentum, so you see the u, and the y momentum, you see v velocity. So d dt, the integral over the volume of u dv, is minus the convective flux, and then pressure gradient, and then diffusive flux. So now these are identical to the differential formulation. So really, this is a div uu, and this is a grad p dot n, and this is a del squared u. Okay? If you don't, you can show this to yourself. You use the divergence theorem, go backwards from the surface to a volume integral. Okay? So they're equivalent. But since finite volume, since we're dealing with finite volume, I want to enforce the idea that these are integrals. Okay? Although the result is going to be pretty much identical to a differential formulation with the finite differences being stored at different locations. But in general, that's not the case when you have strange unstructured control volumes. Okay, so let's start with the mass conservation equation. So it says that the integral of u dot n ds equals 0. Nothing is, everything that's coming into the control volume has to leave the control volume. That's what this integral is saying. And if you remember our control volume formulation, this says that the integral of u dot n ds over this control volume with the cell center is equal to the summation of the integral over the faces of u dot n ds. And that's naturally going to lead us to u east times delta y minus u west times delta y. We did this last time. Plus vn dot delta x minus v south dot delta x. Okay? We did this last time. So if you're not convinced, this is the case, raise your hand right now, because we're going to move much faster. We're going to take this for granted. Okay? We're going to apply the same thing to convective and diffusive fluxes. Okay, now that you're convinced of this, then we can simply apply this. And so if you divide by delta x, delta y, you get this form. And notice that I added an n plus 1 over here. This is enforcing the idea that the fact that we want the new velocity to be divergence-free. Remember, in our previous lectures, we said we apply div u to which velocity? Div u n equals 0 or div u n plus 1? It's div u n plus 1 equal to 0, okay? Because we want the new velocity to be divergence-free. Okay, great. So now, at this point, we don't know we haven't specified where the velocities live. They could, by assumption from the beginning, we may think that they live at the cell centers, but they don't have to be. And the fact that the continuity equation is telling you that, around a control volume, you're surrounded by velocities, and we're going to take the divergence of these velocities and place it at the cell center. Why not naturally place the velocities at the faces of the control volume? So if we store the velocities at the faces of the control volume, it gives us a natural feel of fluid flow, right? There's fluid coming into the control volume, so we put the velocities there. And that's another justification of the staggered grid, another way to think of why the staggered grid arises. Now, the fact that this mass conservation constraint shows us naturally that the velocities can live on the faces. Let's just go and put the velocities at the faces. Okay? So now let's introduce the staggered grid in a more formal setting. So we're going to put the velocities, momentum, and velocities at the faces. Okay? And we're going to place all scalars at the cell center. Now there are several ways to stagger. And when I say several ways to stagger, I'm saying that how do you index, if this is ij, this cell is ij, how do you index this velocity, and the other ones? Is this ij, or is this I minus 1 j? Is this vj minus 1, or vj, or vj minus half? How do you do this indexing? In this class, we're going to stagger to the minus side. So in other words, we're going to say that all momentum, all variables to the minus side, minus faces of the control volume share the same index of the control volume. In other words, the velocity that lives here and the velocity that lives there, they have the same index as the cell center. So if this is cell ij, and I'm putting pij because that's the only scalar we're dealing with, right? So pij lives here. If this is pij, then this is uij to the left, and this is vij. And typically, you'll see this notation. Now, some people stagger to the right or to the plus side. So you have uij and vij. Or some people stagger kind of in a weird way. So you have uij and vij up there. It doesn't matter. As long as you are consistent when you implement your code, it doesn't matter how you stagger. But we choose to stagger to the minus side. It's just a common convention that's used, and that we particularly like it. Okay? So now, that being said, then you can automatically just continue indexing. For example, the velocity on the plus face of the control volume is ui plus 1 j. So we're still at the same j level. So j goes in the y direction, right? But then I, we change the index by plus 1. Okay? And same thing for the v velocity. This is vij. We're staying at the same I location, but then this becomes j plus 1. Okay? Now, this indexing is true to arrays. So when you are dealing with arrays, if you are looping over cell centers, over the pressure, and for pressure Pij, let's say P34, then the left velocity is U34. That's what's great about this indexing. Okay, so we're showing the natural indexing that will arise in the code. Now, in some textbooks and in the description typically of finite volume methods, you'll see indexing like ui plus half and ui minus half. And that has benefits when you're explaining how the method works. But then you have to reset everyone's mind and switch back to ij indexing, which I find can be kind of confusing. So let's start from the beginning and stagger to the left, okay? And we agree now that every time you have ij, this is uij and this is vij. Okay? So now let's go back to the let's do some general definitions. So staggering now implies that we have different control volumes for different quantities. So the same way that we said we're going to store a scalar in the natural control volume when we discretize the grid, we're going to store the scalar in the center. And then we said we're going to store the velocities at the faces. Well, the velocities, they need their own control volumes. Because where do you carry the integral on? Right? So we have so take the u velocity equation. We're going to do an integral over the surface. What surface? Which volume? Is it this volume? No, it's not going to be that volume. It's going to be a different volume for the velocity. I'll show you. So this is called the scalar volume, the natural volume when you discretize the grid. Then the velocities and momentum have their own control volumes, okay, that in this case is centered around the velocities. So in other words, the u velocity has this control volume. Okay? So what we did is, I can use this screen. So what we did, we just staggered. That's why you also call this staggering. We staggered this volume to the left by half delta x. And for uniform structured grids where all the delta x equal delta y, essentially, delta x is constant and delta y is constant, not necessarily equal. But then what happens, these faces, they coincide with the center of the staggered volumes. So the control volume for the u velocity is staggered to the left, and the u velocity lives at the center here, okay? And same thing for the v velocity. It's going to have its own control volume. Because when we integrate the V momentum equation, we have a surface integral. What is the surface there? It's going to be the surface of the V control volume. Okay? And that is the V control volume. It's just a volume centered around Vij. Okay? Now the notation I'm going to follow is going to simplify things. You'll see in the literature people showing these three control volumes. It can be really annoying. We're going to try to avoid that as much as possible. Okay? So now let's go back to the continuity equation. And one thing that helps you when you're deriving the equations is first to draw a cell-centered control volume, okay, and then put the velocities around it, okay, and then ask yourself, what quantity am I integrating? Is it a cell-centered quantity? If it's a cell-centered quantity, stick with the scalar volume. If it's a U quantity or U control volume or X staggered control volume, then draw the X staggered control volume, put all quantities around it, and erase everything else so that you're dealing with one type of volume at a time. This is what we're going to do in this lecture. Now for the continuity equation, it is a quantity that where does the continuity live? Where does the result of the continuity equation live at? Where does div u live at? Where does the integral of u dot n live at? Yes, it lives at the scalar volumes, at the cell centers, okay? So that's what led to the structure, to the staggered grid. So we take the velocities from the faces, and then the result lives in the center. So in other words, this u east, u west, u n, u south, they become the divergence at cell ij is ui plus 1 ui plus 1j minus uij plus vij plus 1 minus vij. Okay? And now something natural arises. It's just essentially you're doing this and this, right? You're taking the derivative. Okay? Is this clear? Okay. So now we're going to attack this one term at a time. We're going to start with the x momentum convective flux. Okay? And the x momentum in convective flux is a surface integral of u, that's the x velocity, times u velocity vector dot n ds. This needs to be carried out on a u control volume, right? This surface is a u control volume. Okay, we decided this from the get-go. So let's see what a u control volume looks like. I'm going to do this step by step here, and then eventually we're going to do it by heart. Okay? So we'll start, like I said, we're going to start with a cell-centered control volume, Pij. That's where you always start, Ij. Okay? And just for the sake of illustration, because we're staggering to the left, I need to pick the control volume. We're staggering to the minus side. I'm going to pick the cell-centered control volume to the minus side. So Pij and Pi minus 1j. Okay? What is the index of the velocity here? Uij. Yes, because Pij, we're staggering to the minus side. So what does the velocity over here, what's the index of this velocity? Ui plus 1j. And what's the index of this velocity? Perfect. Now what is the index of the v velocity here? Vij. Yep, because we stagger to the minus side. And what about this one? Yeah, I minus 1j, but in my slides I have this one. So what is this one? Vij plus 1. Okay, so you start with the reference ij, you draw the velocities, stagger to the minus side, and then from those you just do the indexing. So once you write these two, forget about this. You have this one, what is the next velocity up? It's Vij plus 1, okay? And then the velocity here is Vi minus 1j. And then this makes this Vi minus 1, so from here to here, Vi minus 1, j plus 1. Now, what is the U control volume? What I'm after is find what quantities surround the U control volume. So we said the U control volume is centered at Uij, so I'm going to draw it here in yellow. Do you agree that this is the U control volume? Okay. This is how you build your grid when you're drawing things. Okay? You can start with this, but it's going to take you a minute to think about the indexing, okay? Feel free to do whatever. I like to start like I showed you, okay? Now this is a U control volume. Now, like I told you, what we're going to do, we're going to erase everything else and just take our U control volume, because the U convective flux doesn't have anything else except these quantities surrounding U. It doesn't even care about the pressure. So I'm going to erase everything else and take that U control volume. So you agree now that this is a U control volume, and what surrounds the U control volume are these quantities. Okay? Don't worry how we're going to store these quantities in memory. It's going to be irrelevant. Okay? But this is a U control volume. Agreed? Okay. So now, what does this integral tell us? This is equal to the summation UU east minus UU west plus VU north minus VU south. Correct? That is our standard finite volume approximation times delta y and delta x. Okay? This is clear. This needs to be stuck in your head. Okay? Okay, great. So in other words, this is UU east, UU west, VU north, and VU south. Okay? So now our goal, so now we got the fluxes on the U control volume. Our goal now is to approximate these guys. And we're just going to do standard averaging. So if this is a U cell, then the UI plus 1 cell is next to it, and the UI minus 1 cell is the one to the left. We forgot about staggering and whatever. We're just living in the U control volume world. But as long as you know what these velocities are, because they're going to matter a lot. Okay? So to construct UU east, UU west, VU north, etc., we're going to need U east, U west, V north, U north, and V south, and U south, because we're going to take their products. So let's go ahead and do those. So what do you think U east is, if we're going to just average? No, plus over 2, right? So we're going to take the average. So U east is going to be the average of these two velocities. Okay? And then UU east is this guy squared, essentially. Okay? What about U west? This guy? Uij plus UI plus UI minus 1. So when you drop the j, we're going to assume they're equal. So UI plus UI minus 1 over 2, right? Yeah, that's U west. So UU west is U west times U west. Okay? Now, what about U north? So that's this U. It's this guy plus the guy above it over 2, right? So there's a j plus 1. So U north is Ui j, this guy, or Uij plus 1 plus Uij over 2. Just averaging, okay? I find it useful to use this or like do this, okay? So what about U south? We're going to take this value and the value below it and compute it over here. So simple average, Uij plus Uij minus 1. Now this indexing is going to be true in the code that we are. So as we do the for loop, we're going to be doing j minus 1. So it's really great to do it by hand at first. Okay. Okay. So we still have. So we have U east, U west, U north, U south. We still need V north and V south. Okay. What do you think V north is? Where is V north? It lives over here, right? We said that the integral or the value is the mean value. So it lives at the center of the face. So V north lives here. What can we do with, what information do we have at the control volume, or what degrees of freedom? Yeah. Yes, we have the two V's, so it's just a simple average. Okay? So then, V north is V I minus 1j plus 1 plus Vij plus 1. You cannot do this without a diagram in front of you. When you go program this, print this on like like on a board, you know, and just look at it. Because you can easily screw things up, okay? What about V south? The average of these two things, right? Now, you really don't need to worry about, you know, because about where these live, because over here they look, the velocity V looks like it lives on the nodes of the control volume, of the U control volume. It doesn't matter. It's just an array. But the indexing is correct here. It's relative to the U control volume, okay? So in other words, one way to think about this is for U control volume quantities, I'm going to loop over the U control volumes and make everything in reference to that. For scalar quantities, I'm going to loop over scalar control volumes and access variables relative to that scalar control volume. That's it, very simply. But the indexing is true. So an ij control volume for U, these are the same ij over here. Okay? So if this is U47, whatever that is, this is U37. Okay? This is, sorry, V37. You can grab that from the V array directly. You don't have to worry about how it's shifted. Okay? Okay, so now let's do the Y momentum convective flux is the integral over the surface of V U dot NDS. What volume are we dealing with here? A Y control volume, okay, a Y momentum control volume. Okay, so how are we going to do this? We start with a cell-centered scalar volume, okay, Pij, and because we stagger to the minus side, I'm going to need Pij minus 1, okay? So this would be Uij, and this would be Vij. This would be, you don't have to, you can get it from this one, but you can also think of it as staggering to the minus. This would be Uij minus 1, and this would be Vij minus 1, okay? And then this guy is simply Ui plus 1j minus 1, and this guy is Ui plus 1j, and that guy over there is Vij plus 1. And what's a V control volume? Remember, I'm after the V control volume, okay? This is the V control volume. In this case, pardon me, it is centered around the V velocity, okay? Now, we can erase everything and just focus, take this guy and put it over there. Forget about staggering or whatever. We're just dealing with the V control volume, okay? Same procedure. The Y momentum convective flux is going to have UV east and UV west, and VV north and VV south. And then we know that integral is UV east minus UV east delta Y minus UV west delta Y plus VV north delta X, so the flux coming through the surface, minus VV south delta X, okay? So now we need to approximate the fluxes. We're going to do an averaging procedure. So what do we need? What do we need to compute to get this whole thing calculated? Yeah, so U east, yeah. U east, V east, U west, V west, V north, and V south. 6 quantities, okay? So what is U east? This is U east, lives over here. It's on the, yes, these two guys, right? It's the average of these two guys, okay? U east. What about U west? Average of these two guys, right? It's Uij plus Uij minus 1 over 2. Now, what is V east? Correct, yes. So there's a Vi plus 1j over here, the next V control volume, okay? And then what is V west? Vij plus the one before it over 2, okay, I minus 1j. And then we still have V north. So V north is the average of this guy and that guy, right, the cell centers. And same thing for V south is the average of Vij and Vij minus 1, okay? And you just take, you multiply them, and you compute the flux. So you can do this in several ways. Once we start coding, we'll discuss those ideas. But one thought is to say we're going to loop over the Y control volumes and start constructing the fluxes on the east, the west, the north, and the south, and take the corresponding averages, multiply things together, and put them in the right-hand side. Okay? Okay, what's next? The pressure gradient. We're going to look at the x-dir pressure gradient, so that's dP dx, okay? And this is going to be integrated over what? Don't look here. So the dP dx, where does it live? So dP dx is part of the U momentum equation, right? And everything in the U momentum equation, where does it live? At the U volume, because it's a U equation, right? So remember, scalar quantities, everything needs to live at the scalar cell center, okay? As you are integrating scalar quantities. But U momentum, the result, the final result needs to live at the U center, at the U cell center, not at the scalar center. So dp dx, in other words, better result in something that lives at the U control volume, okay? So for the pressure gradient in integral form, it looks like integral of P dot Nx ds over S. What is this S? It's the U control volume. Why? Because that is going to be added to a d by dt of U, right? So the result of this guy better match where this guy lives. And this guy lives in the U control volume, okay? Be careful about that. Now we're going to take this, use this automatically without going through each step. So this is our general grid layout. Where does dp dx, or the integral of p dot n ds, live? It lives here. And what's so great about the staggered grid is that we have pressures at the faces of the U volume already there. See how things just fit naturally. Because such an intuitive way of doing fluid flow calculations. So in other words, the integral of P dot N ds over the U control volume, so we're going to add up the surface values, and this is going to be P east delta y minus P west delta y, which is just Pij minus Pi minus 1 over, well, times delta y. Once you divide by the volume, you're going to get a delta x. But this is identical to a pressure gradient. dp dx, it's Pi minus 1 over delta x, okay? Is this clear? Everything on the right-hand side of the U momentum equation needs to live at the U control volume center, okay? Not the scalars. Everything on the right-hand side of the Y momentum needs to live at the Y control volumes. Now, once you add a scalar equation like temperature, everything on the right-hand side of the temperature equation needs to live at the scalar cell centers, because that's our agreement. All scalar quantities. What happened? It's like it lost power or something. Yeah, turn it back on. Let's see. Okay. Funny thing, I don't know if you've seen people like tap on electronics when they don't work. You go tap. You've seen your parents do that. I grew up doing that. Do you know why people do that? Yes, but in the past, and the reason is that electronics early on used to be built with evacuated tube capacitors, and so what often happens is that these tubes, they just get loose, and so you go to the TV and you just like tap it on the back and just beat it so that it kind of moves the tube a little bit, and so that it resumes contact. But it's useless now because this is advanced electronics over here. Anyway, so now we go to the Y pressure gradient. What are we going to integrate that over? What's the volume for the Y pressure gradient? The V control volume, yes. This is the V control volume layout. And it just so happens that there is P that lives at the faces correctly. So the integral of P dot N ds for the Y control volume is simply P north delta x minus P west, minus P south times delta x, and then you get Pij minus Pij minus 1. That's essentially dp dy, okay? think of where the quantity, the resulting quantity is going to live at. Okay, and you can't mix apples and oranges. You're doing the U equation, okay, the X momentum equation. All quantities better live in the U control volume, okay? All right. What are we left with? The stress tensor or the diffusive fluxes. That's going to be easy. So the X dir diffusive flux is given by this integral less the kinematic viscosity. That's the surface integral of grad U dot n ds. That's for the U momentum equation. What is this S? It's a, what volume is this? It's a U control volume, okay? So if this is a U control volume, this integral is going to tell us that this is equal to du dx east minus du dx west. We did this at the end of class last week, plus du dy north minus du dy south. We still need to approximate those fluxes, and we're just going to use central differencing. Okay, so du dx east is simply the u over here, which is ui plus 1 minus ui over delta x. And then du dx west is ui minus 1 over delta x. Du dy, what is du dy north? So it's this quantity here. It's uij plus 1 minus uij over delta y. And same thing for du dy south. It's uij minus uij minus 1 over delta y. Okay? And then you put them all together, and you get your standard, essentially, diffusion term. Once you divide by the volume, which is dx dy, you'll get a delta x squared here and delta y squared there. So you get a del squared u, essentially. Okay, but this is coming from the integral again. And the integral form is more natural here because it helps you think of where the quantities live. Okay? I mean, I could derive this equation directly from the differential form for this structured uniform grid. Okay? But if you're not aware of where the quantities live, you're going to screw up. So you better start with the control volume. We surface integral, quantities over the surface, and then how do we approximate these fluxes, okay? Now the wider diffusive flux given by grad v dot nds over what kind of volume? What is the nature of the volume? It's a y momentum control volume, or y or v volume, or y staggered volume, whatever you want to call it, okay? And in this case, we only need to deal with that volume. This is a y volume in green. And this integral is simply dv dx, so dv dx east minus dv times delta y minus dv dx west times delta y plus dv dy north minus dv dy south times delta x, okay? Then we approximate the fluxes in a similar way. Again, the staggering doesn't really show up except at a few cases, but once you focus on the quantity and where it lives, you don't worry about staggering. It's just I plus 1, I minus 1. That's the natural indexing, okay? So dv dx east is vi plus 1 minus vij, okay? And dv dx west is vij minus vi minus 1j. Same thing for dv dy north, vij plus 1 minus vij. And then this should be dv, sorry. And then dv dy south is vij. That's what happens when you copy between your slides, and there's a lot to do. So these should be v, okay? Thank you for catching that, no one. Okay, and then the total flux, diffusive flux, is given by this form, which is a del squared. And once you divide by the volume, you're going to get a del squared v, okay? Okay, so who wants to see a staggered grid that took me a long time to put together? Okay, this is how our grid is going to look like. Now, this is going to be your friend and companion. You're going to print this and put it next to you every time you're dealing with code in this class, okay? What you're seeing here is a domain boundary. Now, I know there's a lot of colors and shapes. Try to kind of disengage from that. And it's hard to see the differences in color on this silly screen. This is green, really, and this is blue, but they look quite similar to me. You see from a distance. They're pretty close. Maybe I'll change the colors next time. Okay, so you'd think that a screen like this would be better than a projector. I think it's the other way around. All right, so this is our computational domain. It looks like a square here, but it can be a rectangle, can be any kind of shape. But for simplicity, we're going to show just a rectangle, a square, and it's designated by this red boundary. Okay. Then we're going to go and say we're going to split this volume into, in this case, into 4 by 4 cells. So you have 1, 2, 3, 4 in the x direction, and 1, 2, 3, 4 in the y direction. Okay? So you say this is Lx over n, okay, rather than nx minus 1, like we used to do with finite differences. Okay? So delta x is Lx over n. Okay? So you have 4 and 4. So that makes your grid. Now, because we're going to be setting boundary conditions, let's from the get-go agree that we're going to need ghost cells. So I'm going to add a layer of ghost cells, shown here in light gray and dashed lines, that designate the ghost cells. Okay? So those are the ghost cells. Let's start with the scalars. We said that the scalars live at the cell center. Okay? And it makes sense to start indexing from the bottom left corner. That's the logical indexing that we humans think of. And that's going to be, with Python indexing, that's going to be 0, 0. Okay? So and we're going to start inside the ghost cell all the way to the upper right corner, which is the other side ghost cell. Okay? And then the rest is history. P00, this is P10, P20, and so on. And this is P01, P02, etc. And the first interior cell is P11, and the last interior cell is P44. So, and this indexing is nice. Some people use 0 indexing here and negative indexing there. I don't like that. I prefer to just go from 1 to n, in the interior, because then 1 to n is always in the interior of the domain. 0 and n plus 1 are outside the domain. Okay? They're ghost cells. Okay, great. We started with we set up the pressures, and these are the P's. So, P11, P21, etc. Just straightforward. Now let's create the staggered grid. Now, I'm not going to show the staggered volumes because I think in our efforts to teach the staggered grid, we show the staggered volumes and you mess up everything. Imagine I'm putting 2 more grids on top of this. It's just going to confuse you more. Okay? So I'm just going to show where the velocities are going to be located. So we said we're going to stagger to the minus side. Okay? So U and V are going to lift to the minus side of the ij cell, and they're going to share the same index. So if you pick any cell, P32, then to the left faces of P32, you're going to have U32 and U3 and V32. Okay? Same thing for any cell. And we start all the way from the bottom. So this is U00 and this is V00, pop, 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 all the way to the end. But notice one thing, that there's some kind of asymmetry in this grid. Because at this line, we have values for the U velocity, but not at that line. Why? Because I chose so. Because in our case, we're not going to need either line, actually. Okay? But in practice, you may need this line as well. So you just add one more velocity here. Why would you need this line or this line is if you are setting a Newman condition on the U velocity. So you may need a ghost cell for the U velocity because you have a Newman condition. But in general, when you have a Dirichlet condition on the velocity, you just set it here, right? Because you have a degree of freedom at the boundary directly. Okay? Same thing for the V velocity. There's a layer of V values at the bottom, but none at the top. You can add one at the top, but we're not going to do that now because we're not worried about Newman conditions on the V or U velocity. Makes sense? Yes?
If you have like a pressure Dirichlet condition, would you just shift the grid and just put the pressures on the...
No. You have to use ghost cells.
Okay.
So like we explained in the previous slide, if you have some condition on the pressure, you'll just use the ghost cell to replicate up to second order the value at the boundary.
Okay.
Okay, you don't shift things around for the scalars. Okay. Okay. Now, the velocities also run all the way, from 0 to nx plus 1, ny plus 1. Okay? And on the interior of the domain, they start indexing from 1. Same thing for the v. So for this grid, the sizing of the arrays is going to be for p, you have nx and y, and you have one ghost cell on each side. Okay? So you have 2 ghost cells in x and 2 ghost cells in y. Okay? So you get nx plus 2 and y plus 2. Okay? Same thing for u and v. You may have to add one more if you choose to put additional values here for u and additional values for here for v. So then you may have nx plus 3 and y plus 2 and nx plus 2 and y plus 3. We can do that. We don't have to because we're not going to be using Newman conditions on the velocity. Okay. Is this clear? This grid is going to be your friend. Don't imagine you're going to be able to do it. Don't be a hero and try to do it by heart. You can't. Okay? So I have to print this every time. I have to look at it every time. I have to draw it every time. I cannot use a previous drawing because it doesn't make sense to me. I have to kind of see it every time and do it by hand. Okay? So you can print this and use it every time or just draw it by hand. Okay? Okay, so now we haven't said anything about how we're going to solve the Navier-Stokes equations. We still have an algorithm that we need to deal with. We learned now about the discretization of the different fluxes, but how are we going to solve the equations? Do we know how to solve them? Yes, the projection method. Come on, it's like you're not learning anything. We know the projection method. Can someone summarize the projection method for me? Okay, before we get to the Poisson equation, what do we do? Not you. Okay, so what do we do? Yeah, u tilde. Well, u tilde minus un over delta t equal, advective minus a plus whatever plus d. So that's equal to a right-hand side, right? So you compute a intermediate velocity field. Now this is not an integral form, but it's the same. Once you do the integration and you divide by the volume, you're going to get a discrete form like this, okay? And then you say un plus 1 minus u tilde over delta t equals minus grad p, right? And then you take the divergence of that, minus div u tilde over delta t equal minus del squared p. And we want this to be 0, so that gives us a Poisson equation for the pressure. Del squared p equal div u tilde over delta t. Correct? And then we solve for p, and then we move p back here and get un plus 1. That algorithm still holds because it has nothing to do with finite volume or finite difference, right? As long as you're computing the gradients and the divergences in a finite volume sense. So what is the divergence in a finite volume sense? It's the integral of u dot n ds. So the divergence of u tilde is the integral of u tilde dot n ds. That's it. Okay? That's what we're saying. This del squared p is really the integral of grad p dot n ds. Okay, that's the integral. But in the end, for this case, they're going to look all the same. Okay? So our solution algorithm is this. So for u tilde minus un over delta t is minus advection plus diffusion. And then we correct u tilde by introducing this un plus 1. And this is what we solve for the pressure. Okay? So all of this holds. Okay? Now let's talk about boundary conditions. So we haven't put the pieces together. I know we showed how we discretize the different fluxes. Once we get to coding on Thursday, we're going to put all the pieces together and see how they fit in. It's going to take us a full lecture to program this in, but it's going to be beautiful. Okay? Okay, so let's talk about boundary conditions. We have walls that can be moving, right? And we have inlets, and those are going to imply, and we have outflows. Outflows, we're going to talk about it. We're going to postpone that conversation a little bit later because it's a little bit harder. But for walls and inlets, we need conditions on the velocity, and those conditions are going to imply conditions on the pressure. Okay? So I'm going to show you how we do this. But I'm going to take special cases. I'm going to take like a left wall or a top wall or a right wall. Then you're going to have to figure it out for the particular situation you're dealing with. Okay? All right. Walls, we'll start with the velocity. We're going to take a wall on the x minus side. So that's the left wall. So remember, the indexing in the left wall, this is going to be I equals 0, and this is going to be I equal 1, right? Because that's the first interior point. So I equals 0 in the ghost cell. Remember, we had P0, 0 at the bottom, and then P1. Okay, so, but at any j. So this is a left boundary. Okay? This is a left boundary over here. And if we're starting P0, 0 over here, this is everything here is going to have an index I equals 0, and this is going to have an index of I equal 1, first interior point, if this is the boundary. Okay? This is the boundary shown in red. So let's put the velocities. What do we have here? U1j and V1j. And then we have here U0j and V0j. Okay? Now, we can also put V0j plus 1. So this is at any j value, and this is V1j plus 1. Okay? So what is the condition in this case? For a wall, we need conditions on U and V. What is the condition on U? What happens at a wall for the U velocity? Nothing is coming in, right? So U is 0. Now, what is so great and powerful about the staggered grid is that it gives you a degree of freedom for the normal velocity here. So what do? We can just set directly this U1j for all j. We can set that equal to 0. Bam. Great, like in the finite difference case. What about the V velocity? What if this wall is moving? Okay, so we're going to say V at this wall is equal to V wall, that's specified by the user. Could be 0, could not be 0. So for the driven cavity, at the top, we're going to have V equals 0, but U equal U wall. Okay? So the tangential velocity is going to be moving. What do? We don't have a degree of freedom for V over here, but we have V on the interior and V in the ghost. So what do? Yes, average. We use the ghost cell. We say V interior plus V ghost over 2 equal V wall. So up to second order, this will give us a specification for the moving wall velocity. Now, in terms of this indexing, the first condition implies that U1 j for all j is equal to 0, and that the second condition, V equal V wall, implies that V0j plus V1j for all j. Okay? So these guys, the average is equal to V wall. These guys, the average is equal to V wall. So essentially, you can slice through this in one chunk in Python. Okay? I'm going to do the same thing for a top wall, just to kind of help you fix the ideas in your mind. So for a top wall, forget about this mess here. Let's just focus here. For a top wall, we reach the maximum indexing in our indexing. Okay? So this cell is PINY. That's the last interior cell. Remember, interior goes from 1 to n. So 1 to ny, all the way up. And then this ghost cell is PINY plus 1. Okay? Because we stagger to the minus side, this is UINY, this is VINY, and this is UINY plus 1, and this is VINY plus 1. And these guys automatically, you can deduce those automatically. At a top wall, what happens? The V, there's no normal flow coming in, so V is equal to 0. And looks like we just have V living on the boundary. So we can set that directly to 0. So VI and Y plus 1 for all I is equal to 0. So all of those V's over here are equal to 0. Okay? Now, what about the U velocity? We don't have a degree of freedom for U at the surface. Okay, and if this wall is moving, we're going to have to set a value. It could be 0 either. what do? We average. So we have u's over here, and we have u over here. We just take an average. So we say u interior plus u ghost over 2 equal u wall. And in this case, this is saying ui and y plus 1 plus ui and y for all I over 2 equal to u wall. Okay? So in other words, the specification at a wall is always normal velocity equal to 0, u dot n equal to 0, and the tangential velocity is specified, u dot t, the tangential component of the velocity, in other words, v in this case. It's v wall, v or u depending on what boundary you're at. You just use a ghost cell specification. Now the indexing here is going to change depending on what side you're at, okay? And you're going to have to figure that out when you code, okay? That's why boundary conditions are usually the hardest part of the code if you want to deal with general boundary conditions, okay? Luckily for us, we're going to be hard coding things, so as we write the code, we're going to say, oh, you know, at the left boundary we have this, so let's just set it directly. Okay, now what do walls imply for the pressure? Okay, I'm going to take a left wall, so that gives us back this simple indexing. It's always easier to show an example with indexing 1 and 0 rather than ny plus 1 and x plus 1, because you have to speak a lot. Okay, so this is a left wall. Again, first interior point, the index I is 1, and the ghost cell index I is 0, and this is at any j. And you know, since we're staggering to the minus side, we have all of these indexing set up, so I hope you agree with this. So what are we going to do with the pressure? We said there are several ways of dealing with the pressure. One way is to say that if you know the velocity at the boundary, you say that there is no correction for the velocity. So in other words, un plus 1 is equal to u tilde, therefore grad p is equal to 0. That's not a very strong way of stating this problem. So let's try to find another boundary condition for the pressure. And this is where the power of the staggered grid shines, just by placing the velocities at the surface of the control volume. What we're going to do, we're going to apply mass conservation. I don't care about mass conservation in the ghost cell, right? So the first cell that's interesting where we have a mass conservation makes sense is this interior cell over here, because it has a boundary condition, and somehow the pressure needs to sense this boundary condition and communicate with the rest of the domain to enforce mass conservation correctly. Okay? So we're going to take this cell and apply mass conservation, because we want to know what we're going to set for the pressure in this cell. So we're going to apply continuity equation, and since we derived this earlier, this is just simply telling us u2j minus u1j over delta x plus v1j plus 1 minus v1j over delta y equals 0. That's essentially du dx plus dv dy equals 0, lives at the cell centers. Okay, let's move this. But we know that u1j n plus 1 is equal to 0. It's given to us, correct? So this implies if we set u1j equal to 0 over here, this simplifies the continuity equation in this cell to this thing. Okay? Now, how can we convert this to something related to the pressure? We're going to say now, because we said from the beginning that un plus 1 is u tilde minus delta t dp dx. And dp dx is evaluated at uij. Okay? So for any uij, this dp dx lives at uij. So in other words, we have u2j here. We're going to be doing a dp dx over here. And for for these v's, we're going to be doing dp dy and dp dy. Okay? So let's go and take this thing and substitute it over here. Okay? So u2j n plus 1 is u2j tilde minus delta t grad p, which is p2 minus p1 over delta x. Okay? v1j plus 1, which is this guy, is going to be v1j plus 1 tilde minus delta T dP dy. And dP dy is P1J plus 1 minus P1J over delta Y. Okay? Same thing for V1J. It's V1J tilde minus delta T dP dy, which is P1J minus P1J minus 1 over delta Y. Okay? I haven't done anything fancy. We're following. Everything is logical. Okay? So you go ahead and collect and simplify terms together. You actually get an equation for the pressure at the boundary. Why is this an equation for the pressure? Because we know what U tilde is. We just computed it in step 1. Right? Remember, the next step after we compute U tilde is to calculate the pressure. Now, what is this doing? Contrast this to what we said our pressure equation is. It is the same, it is the pressure equation, nothing more, except that it's modified a little bit at the boundaries. So rather than having the full stencil of the coefficients 1 minus 2, 1 minus 2, and 1, and 1 minus 2, 1, we just skip one of the terms for the pressure. That is what is so great about doing it this way. So in other words, the pressure in the ghost cell, before I get to in other words, does the pressure in the ghost cell show up anywhere here? It doesn't matter. Doesn't matter. So what we do in practice, we just set it to 0 because we don't care about it. Doesn't matter. Okay? Because it doesn't show up. We don't need it. Okay? So the coefficient for the Laplacian in this cell, for this pressure, is going to be, there's no connection to the outside pressure. Okay? So in practice, what you do, when you form your pressure equation or your pressure coefficient matrix, you go at the boundaries and say, hey, do I have a solid wall here? If I have a solid wall, I'm going to kill the pressure, the coefficient for the pressure that connects it to the outside. So you start by forming the pressure equation as a standard Laplacian, assuming there's values everywhere, and then you go at the boundaries and fix coefficients. Okay? Okay, let's do an inlet next. So we're going to take the x minus side just for simplicity. These same procedures you should be able to apply at a plus side, at a plus x, minus y, or plus y side. Okay? So again, for a inlet velocity on the minus side, typically the specification is that the normal velocity is given, you're given a value for the normal velocity, right? So you can directly specify this at the boundary, which is great. You can directly specify u. But what if your flow is coming at an angle? So you're bringing in u, but you're also bringing in some v. So you could have a value for v as well. Okay? So then what if v is also v inlet? What do? We don't have v at the boundary. We only have v at the interior and in the ghost cell. So we average. Pretty simple, second order approximation. So v interior plus v ghost over 2 is v inlet. So in other words, walls and inlets, they're not different, really. It's just setting, so you can unify the treatment for walls and inlets into one formulation. That's what we do in our research code, Wasatch. Walls and inlets, we don't distinguish between them. It's just a value, and then we do the treatment correctly. If the value is 0, that's 0. It's like a wall, okay? For the pressure, the same thing happens, except now, so we're going to take the continuity equation and replace the u value with a fixed value. And then do the pressure, and then move all known quantities to the right-hand side. I'm not going to derive it here, but in other words, what happens, you modify the stencil, but then you have a known value that you move it to the right-hand side of the pressure equation. Okay? And this is it for today, because we're not going to have time to start coding this right now. I don't want to break the line of thought. So on Thursday, we're going to sit together and do our first finite volume staggered grid solution of the Navier-Stokes equations. And we'll show that it's going to enforce continuity discretely. We're going to apply it to the lid-driven cavity problem. And then we're going to introduce your project 2. We're going to discuss some ideas about project 2, what you want to do. You can certainly redo what you did with the vorticity stream function, but that's a simple problem now, right? Because you're so advanced now in your mental capacity to understand all of this mess, okay? But coding this may take us the entire lecture on Thursday. Make sure you bring your laptops and coffee or tea or juice, whatever you're interested in, okay? Okay, do you have any questions?
Would you have to use pressure go cell?
In no, you won't, because that u velocity, so in other words, if I go back to the wall case, un plus 1 is known. You just move it to the right-hand side. But I see what yeah.
Because this case is intuitive to me, because it's like if you have
A wall,
obviously
there's
the pressure isn't going to,
yeah.
the outside pressure isn't going to affect the
Yeah.
inside pressure because it's a solid barrier. But if you have an inlet, then
I mean, you can deduce so naturally, boundary conditions are going to be applied on the velocity, and they imply a pressure boundary condition. If you are given a pressure, sorry to interrupt you, but if you are given a pressure value, you have to figure out a way to move from pressure to a velocity boundary condition.
you're using
Okay?
the velocity boundary condition to give you the pressure.
Yes, using that. In other, I know what you're saying. You're probably thinking, okay, what if I apply a pressure at the inlet?
Well, I was trying to
you have,
think of it intuitively, like
yeah.
this is intuitive to me, but yeah.
When you have an inlet, I know, yeah, it's gonna, but the math doesn't fly, right? You just move it to the right-hand side. Now, is that gonna imply a pressure value in the ghost? Yeah, it's gonna imply a pressure gradient at the inlet, which is gonna be dictated by the dynamics of your entire flow. Okay, it's gonna imply a pressure gradient at the inlet, right? That's essentially, you can think of it as driving your flow. But
Using the velocity
to set that, yeah. Okay. Okay. Any other concerns? Question now. Who's seen the staggered grid before, or kind of informally you've probably heard? Well, some of you have heard of the staggered grid, but this is kind of now you know true CFD, and the hope in this class is to really teach you all you don't learn CFD unless you write a CFD code, and then you may never have to write a CFD code in your life, okay? But I think it's a worthwhile exercise, and then you can use all the commercial software you want, but one day you're going to be thinking like, yeah, this doesn't make sense here, and you're going to question what are they doing at a pressure boundary condition. If Fluent allows you to set a pressure boundary condition, well, that really doesn't make sense because your natural boundary conditions are going to be on the velocity, okay? So Fluent actually deduces a velocity boundary condition from the pressure.